This subsection is really kind of an extension of the last one, except that there are some techniques that we can use, and that's where we're going to focus on, what we're going to focus on in this video. Remember I think it was early in the previous video, I said if you had an equation like, I don't know, y equals 3x cubed minus 7x, I'm making a kind of a big nasty one on purpose, 7x squared plus 12x minus 1, you could write parametric equations for that very easily. All you have to do is let x equal t, and then y is 3t cubed minus 7t squared plus 12t minus 1. All right, but that's the trivial case. That's the least interesting possible set of parameters or set of parametric equations that we could use to define this Cartesian equation. Now, we're not going to be doing anything like this complicated, but I wanted to make the point that there is always one. It's just not always very interesting. The methods described in your textbook are method 1, solve the x equation for t, and then substitute that t equals whatever into the other equation. We did that in the previous video. The second method is solve the y equation for t. And we did that in the previous video as well. You said you change y of t equals to y equals, solve it for t, and then take your t equals whatever you find for t, and plug it into the x equation. We did one problem two different ways. Well, we solved the x equation for t and plugged that in, and then we solved the y equation for t and plugged it in reverse. We did one problem both ways in the previous video, so I'm not going to repeat that here. One thing I will say, and your textbook does not talk about this, is that I'm going to make up some parametric equations here, make up a system. Let's say we have 3e to the t minus 2t, and y of t equals t, or 2 minus t. So we have an ugly equation. It's got an exponential function in it. And we've got an easy one, a linear function. This one's going to be easier to solve for t. So whether you have an exponential function or a sinusoidal function, a trigonometric function, doesn't really matter. If one of them is linear, that's going to be easier to solve for t. In this case, the x equation is linear, so that one's going to be easier. It's not quite as easy to solve for t as this one because it has a coefficient in front of t. It's going to give you a fraction, but it's still going to be easier to solve for t and then substitute than it will be to solve this one for t. That's for sure. Now, they won't always have one linear equation. Sometimes they'll both be quadratic, or one will be a quadratic and the other will be a logarithmic. We don't need to worry about that too much in this class because you're not really going to see a lot of those. This is really just an introduction to the idea of parametric equations. We will be doing a lot more with parametric equations, but we're not going to spend a huge amount of time eliminating the parameter, basically, finding ways to write Cartesian equations from parametric equations. So I think that's really enough for this video. In the next one, we're going to be looking at finding parametric equations for curves defined by rectangular equations. And what that means is finding a way to write a pair of parametric equations if you're given a function y equals stuff with x in it. This is the standard way we're used to seeing functions. If I give you this, can you write something that looks like this? And that's the next video.